Hello everyone and welcome to the first lesson in the Principles of Engineering course on simple machines. In this lesson, we're going to be talking about how to calculate the ideal mechanical advantage, the actual mechanical advantage, and the percent efficiency of the 6 simple machines found in our world. And this is going to help you be able to create mechanisms that will manipulate force and distance in the way that you need to get the job done. So let's get started. So as said earlier, there are 6 simple machines that can be found or designed for. And they are the lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. Now, simple machines are used to give us mechanical advantage. And mechanical advantage is a pretty powerful tool or a pretty powerful concept because it can be used to manipulate things like speed, distance, force, and alter the function of the mechanism itself. It's important to note, though, that regardless of the mechanical advantage that you give, you're still performing approximately the same amount of work. Now, that's assuming no friction. So you're not necessarily getting out of doing work. You're just manipulating the force and distance that it takes to get the job done. So let's talk a little bit about what is work. The amount of work you put in a system is equal to the force times the distance parallel. So if we draw a box here, and this box is going to be traveling along the ground as shown here, and we apply a force parallel to that ground, so it's going to be pushing it horizontally. We can calculate its work. Now, let's say we have a 50-pound force, and we push that box pretty far, and that distance is equal to 10 feet. The work is pretty simple to calculate. It's just the product of the two numbers, 50 pounds multiplied by 10 feet. And that's equal to 500 pound-feet of work. So that's how you can calculate the work in a system. And like we said, no matter the mechanical advantage you put into the system or you get with your simple machine, you're not changing the amount of work. That stays the same. You're just manipulating force and distance. Make it easier, but you have to give more distance, or vice versa. Make it harder for yourself to push more force, but less distance in the long run. And that's kind of the beauty of the simple machine. And that all stems from mechanical advantage, which we're going to discuss next. So with calculating mechanical advantage, it's important to note that there are 2 different types that we'll be dealing with. The first type is the ideal mechanical advantage, or the IMA. And these are theory-based calculations where friction is not considered. So this is important to highlight here. Friction is not considered in any of these calculations. So we're dealing with 100% efficiency with these mechanisms. So we use this primarily for determining efficiency, which you'll see later, and the safety factor design calculations. So you can approximate what a mechanism or a simple machine is going to do for you based off of its IMA. And then you can make approximations on how much you're going to lose later down the road due to friction. The IMA is the ratio of the effort and resistance distance as shown by this equation here. dE being the effort distance and dr being the resistance distance. The second type of mechanical advantage is the actual mechanical advantage, or the AMA. And this is an inquiry-based calculation where friction is considered. So that's the big difference between the two. IMA doesn't consider friction, where AMA does consider friction. And so this is going to be lower. AMA is always going to be lower than the IMA. So we use this primarily to get our efficiency calculations. You're actually truly measuring the forces it takes to work with your simple machine. And you can use that to gather the percent efficiency for later designs. We calculate the AMA using, like I said, the forces, and it's the ratio of the effort force with the resistance force, as shown in the equation here. Now, using these equations, you're going to find that sometimes you get a mechanical advantage equal to 1, sometimes you get it greater than 1, and sometimes you get it less than 1. And so it's important to note what each of these mean when you see them or when you're trying to design for them. So let's say you design for a mechanical advantage equal to 1. Well, that means there's no mechanical advantage given by the machine. It's kind of that balanced number. It's the magic number that they call it. So really, it's simply a transmission of force. You are performing the same amount of, or needing the same amount of force. You're going the same amount of distance. You just might, instead of pushing up, be pulling down, or instead of pushing right, you're pulling left. You're just changing a direction or transmitting the force to another simple machine that's doing another task. If you do a mechanical advantage greater than 1, then you're looking for strength. So the mechanism is going to take less force to operate, but it's going to take a greater distance to go. And so if you want to give yourself a little bit more power, this is what you're looking for. A mechanical advantage less than 1 is the opposite. It's going to take more force to operate, but it takes a smaller distance to go there. And so typically this is great for precision, okay? Things like tweezers, where you don't want a lot of force in pinching the skin. You're trying to get something that's very fragile out, or manipulate things that are very fragile. You want great precision. So you actually take the force away that you have, and you sacrifice it for a smaller distance that it has to travel, giving you more precision overall with the mechanism. So you see 3 different types there. Equal to 1 is a transmission of force, greater than 1 is for strength, and less than 1 is great for precision. Lastly, it's very important to note that mechanical advantage can never be 0 or less. If you see these values come up when you're calculating or you're designing, there's probably a numerical error in your calculations. A mechanical advantage of 0 means that no work is really being performed with your simple machines, so they're not effective at all. And less doesn't make sense in the grand scheme of the equations at all. The last thing we have to do is we have to learn how to calculate our efficiencies of our mechanisms. And this is really simple. Once you have the AMA and the IMA, the efficiency, or percent efficiency rather, is the ratio of the two. I'm going to put a percent sign here so we see that, because we are dealing with percents. And very, very important, again, to note is that no machine is 100% efficient. So the efficiencies you see will always be less than 100%. If you achieve an efficiency of 100% or more, you are creating perpetual motion and free energy, which then you will receive a lot of awards and probably end up with a lot of money at the end of the day. But for now, we don't know any of those, and so our efficiency should always be less than 100%. Okay, so now that we've gotten through a little bit of the theory, it's time to take a look at the simple machines themselves. So the first one we're going to be dealing with is the levers. And there's actually 3 classes of levers that we could talk about. And so our first class of lever has the fulcrum, or the pivot point, in the center, and it has a lever bar on the top and 2 forces that are manipulating that lever, like so. So the blue we'll call the effort force, and the red we will call the resistance force, like so. With the resistance force, there is the resistance distance, which is the distance from the resistance force to the fulcrum. And for the effort, it's the same thing. It is the distance from the effort force to the fulcrum. And we'll draw that so it's a little bit clearer there, just like that. And so this is the basic structure here of our first class lever. So we can see that the fulcrum is in between the two forces. And this reminds us of the seesaw. So when I think of first class lever, I typically think of the seesaw that you probably have seen on a playground somewhere. The second class lever has the fulcrum now on the end with the lever bar pulling out from it. It has an effort force somewhere towards the end and a resistance force somewhere in the middle. Now, the same rules apply for the distances. The resistance distance is from the fulcrum to the resistance, and the effort distance is the distance from the fulcrum to the effort. So just like we see here, and we'll draw in those values to make it clear. This one I'll have to kind of write a little bit smaller. So we have that. And this lever reminds us of the wheelbarrow. So if you can think about it, you put dirt in the wheelbarrow in the center and you lift it up at the end, and the wheel is really the pivot point, or our fulcrum in that case. The last class looks very similar to our second class here, with the fulcrum at the end and the lever bar coming out, except our effort force and our resistance force are now swapped. So now we have something that looks like this. And again, we're going to put in our distances. Like so. And I believe I'll draw this next one underneath right here. Doesn't matter necessarily where we draw it as long as we can see it. And we'll label these with DE over DR. And so this class here resembles our tweezers. Very precise objects. Okay, so that's actually going to be taking force away from us. That makes it harder, but it gives us more precision. So tweezers is the first thing I think of with the third class. Now, with the first class, the mechanical advantage that you get is a pretty wide spectrum. You can get a mechanical advantage for the first class that is less than 1. You can get it to be equal to 1. And you can also get it to be greater than 1. So you get everything from the first class lever. For the second class lever, it specializes really in one type, and that is the mechanical advantage greater than 1. Now, the advantage of the second class over the first class is that you need a smaller lever arm, or a smaller lever bar here that I show, versus the first class to achieve the same higher mechanical advantage. So if you really, you want a high mechanical advantage, the second class is going to do it for you. The third class is opposite. It's only going to give you a mechanical advantage less than 1, and it's really good at doing that. So again, it's a very effective way using smaller lever arms to be able to achieve a mechanical advantage less than 1. So now that we've seen the structure of the lever, the last concept we need to do before we can actually start calculating our mechanical advantages is the concept of a moment within our lever. So the moment is a turning effect of a force due to a perpendicular distance. Okay, so a very easy thing to do that I usually tell my students is to put a pen on the table right now. And you can do this, you can follow along with me. You put a pen on the table and you're going to put your finger right at one end of it. Okay, and that's going to create your pivot point. And then I want you to push along the pen parallel to the table so that it starts to spin around the pivot. Okay, Well, that spinning force is the moment force. It's the turning effect that you're creating. That spin is what is actually happening with our levers. If you take a look here, you've just created a lever. You have a fulcrum at your pivot point where your finger is holding onto the pen, and you're applying an effort force at the end, causing our lever to spin. And so a moment is being created, and that is a force times a distance perpendicular, and that's going to give us our moment. Okay, so you can see it's a little bit different from what we talked about with work. Now the distance is perpendicular, or creates that T with the force. So we'll see this in calculating our lever example. Lastly, rotational equilibrium, which is what we're going to be achieving to get our mechanical advantage, is going to be the sum of all moments equating to 0. So we're going to take all of those turning moments that we calculate, and we're going to basically set them equal to each other, and they will cancel each other out. So whatever turning moment the resistance carries, the effort is going to counteract. So now we've made it to our lever example. Before we begin, I do want to ask you a quick question. What class lever are we dealing with here? So a few options are going to be showing up on your screen in just a moment. I would like you to answer with your best guess. What class lever is this? And I will get back to you with the answer when you're done. So if you chose first class lever, you would be correct. This is a first class lever, tried and true, because the fulcrum is in the center and the effort force and the resistance force are on the outsides of the lever, acting in the same direction. And so this is the clear definition of a first class. So now that we got that, we are now going to calculate the distance the effort force should be placed for rotational equilibrium. So remember, that's that concept where we're going to take the turning moments caused by these forces and we're going to sum them basically to 0. Another way of thinking that, and that I like to think of it, is to make them equal each other, set them equal. They should be equal and opposite, really. So whatever the effort force and the distance effort is going to cause moment-wise should be equal and opposite to the resistance and the distance of resistance. So it looks like this. You take your resistance distance and your resistance force and you multiply them together, like so. Then you can take your effort force and multiply it by your effort distance. And this will sum our moments up and equal them. Yep, that's just copying. Yep, no. So the second part of the question that we got to answer is we got to calculate the distance the effort force should be placed for rotational equilibrium. So rotational equilibrium is that concept where the moments will cancel each other out. Basically, both sides are going to be balanced. And you can think of the seesaw as being balanced in this case. So what is it going to take to balance my seesaw? To do that, it's really simple to set up. You're going to calculate the moment caused by each force. And so that's going to look something like this. We have the resistance force times the distance resistance, and we have the effort force times the distance effort. Remember, a moment is equal to the force times the distance perpendicular. And in this case, our effort and resistance distances are acting perpendicular to our forces. Because they need to be balanced, in algebra, we can think of that as an equal sign, right? And so we have this equation here, and then we just plug in our numbers to solve for our unknown dE. And so I'm going to give you a minute or two to be able to do this at home. I would like you to plug in the values that you know into this equation, and I would love for you to be able to calculate the value of dE. So to calculate for DE, we're going to plug in what we know. We know that FR is 20 pounds. We know that DR is 2 feet. We also know that FE is 10 pounds, and we do not know what DE is, so we'll leave it just as a variable. On the left side, I'm going to get 40 pound-feet, and on the right side, I'm going to get 10 pounds times DE. So to get DE by itself, I'm going to divide by 10 pounds on both sides. Let me write that unit just a little bit better here. And this is going to cancel out the 10 pounds on the right side, and it's going to cancel out the pounds unit on the left side. So I'm left with just feet, which makes sense. And 40 divided by 10 is equal to 4. And so I am left with 4 feet. And so conceptually, I want you to think about this. We can balance out a 10 and a 20 pound weight on a seesaw just by moving the 10 pound weight double the distance. Okay, so essentially it only takes me half of the force to balance out if I double my distance. And so really this mechanical advantage in that concept is equal to 2. Our next simple machine is the wheel and axle. And really a wheel and axle acts like a lever. And it could be a second class or a third class lever. So I'll just draw one of those. And it's allowed to act in a 360-degree fashion. So something like that. Okay, probably a little bit better drawn, but something relatively like that. And so with the wheel and axle, there's really 2 cases that you could be dealing with. So I'll draw them a little bit better out like so here. The first case could be that the resistance is towards the axle and your effort is towards the outer part of the wheel. Something like this. The other case is that the resistance is towards the outer part of the wheel and the effort is placed on the inner. And really what they equate to, if you think of it in terms of a lever, is it really makes our second and third class levers here. So the first one acts as a second class, and our next one acts as the third. So nothing new here. Same concepts. And you'll see that the IMA is going to be very similar to how we calculated it before. Now, this first one resembles really our hose valves here. A lot of people will probably relate to that. We've all probably seen this hose valve to turn on and off the water. The second one you can think of as a wheel from a car. Okay, wheels in a car, when they're connected to the drive shaft, that's what's going to help spin these wheels and get them going forward. The axle in the center is actually what's driving the wheel itself, and so you have that axle driving the wheel kind of scenario. So to calculate the IMA of a wheel and axle, it is dE over dR again, but that could be simplified to be the effort diameter over the resistance diameter. This comes from the fact that the effort distance truly is the circumference, and that's just pi over, or it's going to be pi times diameter. And same thing here, it's going to be pi times diameter of the resistance. And so you can see that the pi's are going to cancel out in this scenario, leaving you with just the diameters left, which is where I have it here. So you can just think of it effort diameter over the resistance diameter, and you'll be good to go. So that's going to lead us now to our next example, which is the wheel and axle example. In here, we have an industrial water shutoff valve designed to operate with 50 pounds of effort force. the valve will encounter 200 pounds of resistance force applied to a 1.5 inch diameter axle. What is the required wheel diameter to overcome the resistance force? And we're going to assume 100% efficiency here. So before we start, I would like you to draw out at home what you think the diagram of this system should be. What should it look like? Where should the effort force be? Where should the resistance force be? What does that wheel look like in total? So I'll give you a couple minutes to do that, and then we will draw it together. Okay, so hopefully you've given this a shot. So let's see how well you did here. For the industrial water shutoff valve, I'm just going to draw my outer part of the wheel here, and I will draw my smaller part of the wheel in the center, or the axle rather. So this is designed to operate with 50 pounds of effort force. It doesn't say exactly where, so let me move on. The valve is encountering 200 pounds of a resistance force, and this is applied to a 1.5 inch diameter axle. So this does tell me where the forces now are located. So I know I have 200 pounds of resistance at the axle, and I know the diameter of this to be 1.5 inches. So that means that my resistance, or it's going to be my effort force, is on the outside here, and it is going to be 50 pounds. So this is our free body diagram for the wheel and axle example. So if you got it right, congratulations. So the second part of the question here we're going to solve is, what is the required wheel diameter to overcome the resistance force assuming 100% efficiency? So now we have to take a look at the concept of AMA to help us solve this. Really, behind the scenes, it's just another balancing act, just like we saw with the lever, but this is a great place to bring in AMA. So to calculate the AMA of the system, right, we are going to do FR over FE. And so that is going to be 200 pounds over 50 pounds, which is equal to 4. And this is unitless because the pounds cancel out, and all these ratios will be unitless. Okay. Now, 100% efficiency means that your IMA is equal to your AMA. It basically says there is no friction. Okay, so in an ideal case. That means that my IMA is equal to 4 as well. So with that now being said, we can solve for my wheel diameter or my effort diameter that I need. And so IMA is equal to DE over DR. And I have all of the tools I need to now solve for my DE. So now I ask you, take the next minute or two, and I would like you to solve for DE and see what you get. And we'll see how well you did in a couple of minutes. Okay, so finishing it up here, as we said before, IMA is equal to 4, so we'll plug that in. I don't know DE yet, so I'll put that as DE. And DR is 1.5 inches. And so if I multiply 1.5 on both sides, and the inches will carry over, I am going to get DE equal to 6 inches.